Good morning, students. So, as a part of the discussion of pharmaceutical chemistry, today's topic is applications of resonance of chapter 1. So, here we are going to discuss how the resonance influence the basic character and acidic character of organic compounds. Particularly, how the resonance influence the basic character of amines means the resonance may increase the basic character of the amines or decrease the basic character of amines, as well as the resonance increases the acidity of alcohols or decrease the acidity of alcohols. Those are the things we are going to discuss about today with some examples. Right. So coming to the applications of resonance, first I will discuss about the basic character of amines. Basicity of amines. First, the point is what is a base? The tendency of donating a pair of electrons. Tendency of donating a pair of electrons, that is called as a base. Example, ammonia have a lone pair over the nitrogen. This lone pair is readily available. To donate. Therefore, this ammonia behaves as a good base. Right? So, in the case of, if you take any group besides the ammonia, let's say methylamine, this is called as the methylamine. When we compare to the amine, this methylamine is strong base because this methyl donate electrons to the nitrogen and more electrons are available here. When compared to the ammonia. So, this is a strong base when compared to the ammonia. So, like those things generally, so we have discussed under the properties of the inductive effect. But today we are discussing about the property of the resonance. Right. Now we discuss how the resonance influences the basicity, whether the presence of the resonance increases the basic character or decreases the basic character. Right. So, this is called as aniline, right? Phenylamine. This is also called as the phenylamine. Next, coming to this is benzylamine. Now we have two compounds, one is the aniline and the another one is the benzylamine, which is more basic among these two. Right, see here coming to the aniline, the first case, the aniline having a lone pair of electron on the nitrogen. The benzylamine is also having a lone pair of electron on the nitrogen. Now we have to see which lone pair of the nitrogen is readily available to donate. Obviously that is the more basic in nature. Coming to the aniline, this lone pair is in conjugation with the double bond. When the resonances exist, must contains the conjugation. The double bond must be having an alternative position of the double bond. A double bond should contain a lone pair in the alternative position. A double bond should contain the positive charge or negative charge in the alternative positions. Then obviously it shows the resonance. Now see here, this double bond is in conjugation with the lone pair of the nitrogen. Then this lone pair is participate in the resonance. This lone pair is participate in the resonance. So therefore here in this resonance exist. In this resonance exist. Lone pair not available. Lone pair not available because the lone pair is readily participating in the conjugation or the resonance. Then how could it donate that lone pair? If there is no lone pair, there is no static lone pair, that will not readily available to the donate. Once it is not donating a pair of electrons, then it is not defined as a base. Coming to the benzylamine. In the benzylamine, we have the lone pair on the nitrogen as usual in the aniline case. But this lone pair is in not conjugation with the ring. The lone pair not in conjugation with the ring. Then here there is no question of the resonance. Means here no resonance. Once there is no resonance means this is readily available. Lone pair readily available. Lone pair is readily available. Right? So lone pair is readily available. Therefore, strong base are more basic in nature. Strong base. This is a weak base. So like that we can correlate. Now finally, hence it is proved that resonance decreases basicity of amines. Resonance decreases the basicity of amines. So I can compare one more example here. In between these two, we have NH, CH. Methyl aniline. This is a methyl aniline. So methyl substituted aniline. Methyl substituted aniline. So as in the previous case, this lone pair must involved in the conjugation. A resonance possible. Resonance possible. But additionally, it is having one advantage over the aniline is methyl group. Methyl group is positive resonance effect group. Positive resonance effect group means the methyl donate electrons towards the nitrogen. So once it is acting as the electron donating group which donate the electrons to the nitrogen, then this lone pair, there is a chance of availability. Chance of availability of electrons on nitrogen is possible. Therefore, this is the first case in the basic rank. This is the last race because In the second and in the first and third case, both cases resonance possible, but in the third case additionally we have a electron donating group. Therefore, there is a chance of availability. I am not sure. There is a chance of availability of free electrons to donate. But in the first case, actually there is no choice. So therefore, the second case, the second rank will be given to the methyl aniline. So that is about the basic character of aniline. So finally here what I am going to say is the resonance decreases the basic basicity of amines. Next, coming to the second one, coming to the acidity of phenols. Acidity of phenols. So this is an important property under the resonance, how the resonance will influence the acidity of phenols. We know that phenol this is the structure of phenol. This is the structure of phenol, right? The phenol is a class of alcohols. Phenol is a class of alcohols. Alcohols are weak acids. Alcohols are weak acids. So as the alcohols are weak acids, so therefore phenols, once they are comes under the alcoholic family, obviously phenol should behave as a weak acid. But here the phenol is acting as a strong acid in general. How will you justify why phenol is a strong acid even though that comes under the alcohol? That will be better explained by the concept of resonance, right? So what is a acid generally? The loss of H plus is called as the acid. What happens once the phenol, this is the phenol, if phenols lose proton H plus, then it turns to the oxide minus. Now this is a phenol. This is phenol. This is phenoxide ion. Phenol, when phenol lose its H plus ion, then it is turns to the phenox ion. Means losing H plus means that is called as the acidity. Phenol loses H plus ions to give phenoxide ion. So here this phenoxide ion is stable. Phenoxide ion is more stable than the phenol, right? Phenol lose its H plus ion to give phenoxide ion. Means when phenol lose H plus ions, it is attaining stability. It is attaining stability. This is less stable or unstable. Less stable or unstable. And phenoxide ion is more stable. So that indicates phenol attains stability when it lose H plus ions. When it lose H plus ions, when a substance lose H plus ions, that is called as the acidity. Means phenol shows acidic character. What is the evidence for it? Now we have to discuss about how the resonance. why the acidic character increases means we are once discussing about the resonance, how the resonance will increase the acidic character of phenols. We can better explain this concept by using the resonating structures of both. First, we will discuss about the resonating structures of phenol. Resonating structures of the phenol, right? The phenol. This lone pair is in conjugation. Lone pair is in conjugation with the double bond. Then this double bond. Then the double bond is forming between the oxygen and carbon. OH. The positive charge develops on the carbon. Now the electrons are shifted here. Now these electrons will delocalize into next carbon. Right? Next, like that, resonance is continuous. Finally, right, these are the structures. So we have the resonating structures, number given 1, 2, 3, 4, 5, right? So we have 5 resonance structures are possible for the phenol. Generally, according to the resonance rules, we have some resonance rules. As the number of resonating structures obviously increases, as the number of the resonating structures increases, the stability increases, right? Now we have to write the same resonating structures for the phenoxide ion. Phenoxide ion, right? Now take the phenoxide ion into the consideration. O minus, the negative charge on oxygen. Here, this is a phenoxide ion. Now, again, this negative charge is in conjugation with the double bond of the ring. Comes here. So, the same resonating structures are possible here. Double bond is forming between the oxygen and carbon. Previously, that is a single bond with the oxygen negative charge. The negative charge of the oxygen is involved in the resonance to form a double bond. Then the delocalization continues like in the previous case. O minus. Now the numbering 1, 2, 3, 4, 5. So now we will compare. First point is the compound which exist or exhibit more resonating structures, so that is said to be more stable. But in this case, the phenol is shows the 5 resonating structures, and the phenoxide ion is also showing the 5 resonating structures. So that will not decide. The number of resonating structures may not decide the stability of phenol or phenoxide ion. Now coming to the second law, charge separation should not be possible on the resonating structures. What is the meaning of the charge separation? For example, we have the 5 resonating structures of the phenol. We can't able to find a charge separation on any one of the resonating structures. What is the charge separation means? The existence of the positive charge as well as the negative charge. So we will observe both the resonating structures. Coming to the resonating structures of the phenol, in the case of the resonating structure 1, that is the basic structure, so no charge will be appeared on that. Coming to the resonating structures of the 2, the phenol, resonating structures of the phenol, the second resonating structures of phenol, structure of the phenol. Here see, the oxygen is bearing the positive charge and the carbon is bearing the negative charge, right? So means the charge separation is present on the second resonating structure of a phenol. This charge separation will destabilize the resonating structure. The same charge separation will be observed for the resonating structure 2, resonating structure 3, resonating structure 4. The resonating structure of 2, 3, 4 of phenol causing the charge separation. The charge separation will reduce the or destabilize the resonating structures stability, right? That is the case observed in the phenol's resonating structures. The same charge separation will not be observed in the case of the any resonating structure of the phenoxide ion C. The first and the last resonating structures are having the negative charge, including all, not only these two, all the 5 resonating structures bearing only negative charge. Only negative charge means there is no charge separation present on that, right? So that is fine in the case of the phenoxide ion, right? The charge separation is possible in the phenol, but the same was not observed in the case of phenoxide ion. And one more important point is that if you observe positive charge on highly negative atom, that is also the reason for the destabilization of the any resonating structure. In the case of the resonating structures of the phenol, you can observe the same resonating structures 2, 3, 4. There is a positive charge here, positive charge here, the positive charge here. Means oxygen is highly electronegative atom, and the highly electronegative atom with the positive charge, that also destabilizes. Right? That is, the condition was not satisfied by the phenol. Next, coming to the resonating structure of the phenoxide ions. Here the negative charge is present on the oxygen in the first and last, and there is no charge on the remaining resonating structures oxygen, right? Here this case also satisfied by the phenoxide ions. Hence the phenoxide ions are more stable. This is less stable or unstable. That is, we have written here. Phenol is less stable, phenoxide ion is more stable. So this concept was satisfied at the evidence that can be explained by using the concept of resonance. So resonance increases the acidity of phenols, right? So that is about the acidity of phenols. Last point, one more thing is the comparison of acidity of phenols and carboxylic acids. Phenols and carboxylic acids. We know that we know that carboxylic acids are carboxylic acids are more are strong acids when compared to the phenols. Phenols are weak acids when compared to the carboxylic acids. Phenols also strong acids, but when we comparison in the comparison statements, the phenols are weak acids than carboxylic acids. What is the justification for that? How will you provide? How will you prove? What are the evidence? We already seen the resonating structures of the phenol or the phenoxide ions, right? Now see, we will discuss the resonating structures of the carboxylic acids. C double bond O O H. The R group may be whatever it may be. We can write the methyl, phenyl, whatever group. So we are not focusing on that. Just we are focusing on the carboxylic group. Once it is acting as a base, readily loses the H plus ion, and that is converting into C double bond O O minus. C double bond O minus. This is called as carboxylate ion. This is called as carboxylate ion. Now we have to compare between the carboxylate ion and phenoxide ion. Carboxylate ion and phenoxide ion. We have to write the resonating structure of the carboxylate ion as well as the phenoxide ion, and we need to proceed through the rules of the resonating structures. Then we will decide which is more stable. We already gone through the resonating structures of the phenoxide ion. In the case of the phenoxide ion, there is no charge separation is present, and there is no positive charge on the highly electronegative atoms. Now we will discuss about the resonating structures of the carboxylate ion. Resonance of carboxylate ion. R C double bond O O minus. Right? Here this negative charge on oxygen is in conjugation with the structure 1, structure 2. Right. Now we have to discuss in the previous case what happens. For the phenoxide we got the 5 resonating structures, but this carboxylate we got the only 2 resonating structures. Once we discuss that if more number of the resonating structures are exist, then obviously that is more acidic in nature. Before of all these points, there is a gunshot point is there that the identical, if a substance is providing identical resonating structures, that is more reactive or the more stable irrespective of any rule. See here, in the case of the phenoxide ion, the resonating structure 1 and the resonating structure 5, these two are identical resonating structures. See here, this is having the 3 double bonds, this is having the 3 double bonds, the oxygen with the negative charge and the oxygen is the negative charge. So both are the identical resonating structures. But what happens to the remaining three resonating structures? 2, 3, 4. The second resonating structures, we have the two double bonds inside the ring. The same in the case of the 3 and the 4. The negative charge is present on the ring 2, ring 3, ring 4. Then these 1, 2, 3, the resonating structures 1, 2, 3 comes to the one type of class, A and this B. Means in the phenoxide ion, we have two types of the non-identical resonating structures. Two types of the resonating structures are possible. One is the A type, first and fifth. Second one is the B type, 2, 3, 4. Means it is not having identical resonating structure. Non-identical resonating structure. Non-identical resonating structure. But when you comes to the resonating the resonance of carboxylate, the resonating structures of the carboxylate, now this resonating structure 1 and resonating structure 2 are identical resonating structures. These two are identical resonating structure. R group is there, R group is there. Carbon double bond O, carbon double bond O. Carbon single bond O minus, carbon single bond O minus. Identical resonating structures. If you find whatever the number of resonating structures may exist, if you find identical resonating structures, that is unanimously more stable. Unanimously more stable. So therefore, the resonating structures of carboxylate ion is more stable than the resonating structure of the phenoxide ion. Therefore, carboxylic acids are the strong acidic in nature when compared to the phenols, acidic character of the phenols. This is about the basicity of amines, acidity of phenols. So how it influences? The resonance decreases the basic character of amines, and the same resonance will increase as the acidic character of the phenols. In the next class, we will discuss some more properties. Thank you. Have a nice day.
Like, share, and subscribe. Hit the bell icon for more updates.